Hello, I'm Sean Parrish and I'm going to speak about the Truck Airflow Characteristics Final Year project. This FYP aims to quantify and improve the airflow characteristics surrounding heavy road vehicles at highway speeds utilising computational fluid dynamic simulation data. The most notable characteristics that will be examined is the aerodynamic drag of an articulated truck as well as the aerodynamic forces generated on a caravan combination when it is in close proximity to a truck when travelling at highway speeds. This research area has particular relevance to Australian society as road transport is essential for the supply of resources to all communities in this country. Therefore, any improvement in fuel economy would significantly reduce the need for diesel fuel across the transport industry. Examining the airflow characteristics surrounding both vehicles has been included to determine if the fluctuations in aerodynamic forces experienced by the car while overtaking a truck could potentially cause a traffic accident. This comes in response to viewing dash camera footage of where a caravan combination becomes unstable during an overtaking procedure which results in a traffic accident. Aerodynamic drag is proportional to speed and can account for 33% of total fuel consumption for trucks travelling at 53 km per hour, but increases to 50% at 80 km per hour. In addition to this, for trucks travelling at 96 km per hour, aerodynamic drag accounts for approximately 62% of total fuel consumption. In the case of a truck, form drag accounts for approximately 90% of the truck's aerodynamic drag, whereas the remaining 10% is caused by surface drag, therefore reducing the truck's bluff geometry and preventing turbulence in undesirable locations, most notably at the rear of the truck and between the cabin and trailer, could result in significant drag reductions. Known methods of preventing this behaviour include roof-mounted wind deflectors, cabin fairings, side skirts, which are mounted to the prime mover and trailer. The claimed drag reduction for each improvement are as follows: 16%, 6%, 7%, and 10%. In this project, these drag reduction methods will be examined, with the results being compared to an unimproved vehicle to determine if these claims are valid. Equation 1 depicts the formula required to calculate the coefficient of drag. To further the understanding of airflow surrounding a truck, an overtaking procedure will be replicated in the CFD software in an attempt to determine the airflow characteristics surrounding the two vehicles. Given that most trucks and caravans have flat planar sides, a change in airflow could potentially cause large forces normal to the size of these caravans. This may become apparent when the car and truck are side by side with the caravan and truck sides restricting the airflow, thus increasing the wind velocity and reducing the pressure between the two vehicles. This could be problematic for the caravan combination, especially if it has been poorly loaded, which could potentially cause a traffic accident. In order to develop the required CFD simulations, a number of assumptions and conditions have been established. In the case for the car, truck, and ground surfaces, these have been specified as no-slip smooth walls. The inlet has been specified as having a constant normal velocity that satisfies the kinematic similarity condition that is equivalent to a full-size truck travelling at 100 km per hour. In the case of the CFD enclosure walls and outlet, these have been specified as being at atmospheric pressure. The working fluid was specified as air at 25 degrees and has been considered incompressible. In addition to this, the flow was initially assumed to be steady state, with an RMS residual convergence target of 1 times 10 to the negative 4 being specified. After preliminary studies, the steady-state simulations failed to converge to the specified target, thus indicating that the flow was not steady state. Therefore, transient simulations were required to sufficiently capture the fluid flow. The ANSYS CFX software package has been selected to conduct CFD simulations in. Within CFX, CFD simulations can be solved using two main turbulence models, which are the Reynolds Average Navier-Stokes and Large Eddy Simulations turbulence models. Given that this project involved multiple CFD simulations, the RANS turbulence model was selected, in particular the K epsilon model. This selection was made based on the fact that 9% of the truck drag is due to its form. Therefore, resolving the flow's boundary layer will not significantly affect the final results. The K epsilon model does not resolve boundary layers, but rather uses wall functions, and therefore significant mesh refinement near walls is not required. In comparison to other RANS models such as the K omega and shear stress transport model, as well as the LES turbulence model, significant mesh refinement is required near walls. This mesh refinement near walls will increase the overall mesh element count and potentially result in longer simulation time. Since LES models are used to capture turbulence flows, most notably eddies, which are larger than the local mesh sizing, transient analysis are required, thus increasing the simulation time. The required geometries were generated in Creo Parametric 5. The baseline truck CAD model was generated using photographs and measurements made from a 1/14 scale Mack Granite semi-trailer truck. Using the 1/14 scale CAD model, preliminary studies into the airflow over this truck were conducted. In order for the results to be representative of full-scale models, geometric, kinematic, and dynamic similarity must be satisfied. The use of the 1/14 scale replica satisfied the geometric similarity constraint, but the inlet velocity had to be significantly increased from the 27.8 meters per second required for the full-size truck. Kinematic similarity is achieved when the flow regime or Reynolds number is the same for both models. Therefore, given that both simulations use the same working fluid, and with reference to equation 2, the inlet velocity had to be 389 meters per second. This velocity is larger than the speed of sound for that fluid, which is 349 meters per second. Therefore, compressibility would be apparent in real life, but in the simulation this is neglected by the incompressible flow condition. Once these studies were completed, the CAD model was increased in size to full scale. Using this base model, variations of the basic truck were generated featuring the stated aerodynamic improvements, and then these models were then subjected to various CFD simulations. From the preliminary study, it was found that using multiple fluid domains would allow for greater control over mesh parameters and would allow for greater refinement in locations where the flow was significantly disrupted or turbulent. These locations include areas preceding bluff geometries, the underside and rear of the truck, where in this case, 3 domains were generated, with the inner enclosure having a fine mesh in order to capture the flow separating surrounding the truck and most of the turbulent region at the rear of the truck. For each subsequent enclosure, the element size was increased by a factor of 2, as a need to capture the airflow with such detail becomes unnecessary in locations far from the obstruction. Enclosure sensitivity and mesh independent studies were then conducted to ensure that the final results were not influenced by the enclosure size or mesh. A 5% tolerance on the final drag coefficient value was applied to determine if the enclosure size or mesh were influencing the final result. It was found that an enclosure with a lead of 1.6 meters, a trail of 4.6 meters, a height of 1.6 meters, and a width of 3.2 meters was the minimum required enclosure for the 1/14 scale truck. The largest enclosure elements that were required were 20 millimeters, 40 millimeters, and 80 millimeters for enclosures 1 to 3, which resulted in a mesh element count of approximately 4.7 million elements. The resulting drag coefficient was found to be 0.75. It must be noted that the steady-state simulation failed to converge to the desired RMS residual target of 1 times 10 to the negative 4 and therefore reached the maximum iteration limit of 400. This behavior was potentially caused by vortex shedding off bluff geometries or highly turbulent regions, namely the front section of the trailer and behind the truck wheels. The same processes were conducted on the full-size models. Using the full-size truck, it was found that the minimum enclosure had to have a 16-metre lead, 50-metre trail, a 12.5-metre height, and 15-metre width. For the mesh to be considered independent, the enclosure element sizes had to be 250, 500, and 1000 millimeters for enclosures 1 to 3, with a 125 millimeter face meshing on the truck. Using these enclosure and mesh parameters, a drag coefficient of 0.75 was found, which is the same as the SCAR model simulation. This was to be expected, as the SCAR models satisfied all the conditions required to generate comparable results to the full-size simulations. With regards to Table 1, it can be seen that for trucks A through to H, the drag coefficients found for the steady-state simulations were 0.75, 0.54, 0.69, 0.72, 0.75, 0.51, 0.53, and 0.47 respectively. These figures mark improvements of 28, 8, 4, 0, 32, 29, and 37% over the baseline truck respectively. Therefore, it can be seen that the addition of the roof-mounted deflectors is the most effective in reducing aerodynamic drag. Since the cabin fairings and trailer side skirts fail to record aerodynamic improvements greater than 5%, it is difficult to state whether these additions have reduced aerodynamic drag. The issue being that during the enclosure and mesh sensitivity studies, a 5% limit was specified, and therefore any value less than this will mean that the increase is insignificant. These figures are potentially valid, as modern aerodynamic trucks can have drag coefficients that are approximately 30% less than older, more boxy designs. Since these results were from steady-state simulations which failed to solve, transient simulations were conducted to accurately capture the flow. The resulting drag coefficients were 0.79, 0.59, 0.71, 0.77, 0.77, 0.52, and 0.51 and 0.47 for trucks A through to H respectively. The respective drag coefficient improvements over truck A were 29, 10, 3, 3, 34, 35, and 41%. These results are comparable with the steady state results, as most lay within a 5% margin, with the exception of truck B, in which the steady state and transient results variate by approximately 7%. When comparing truck A and truck H's pressure and velocity plots, it becomes apparent that the aerodynamic improvements significantly reduce the pressure concentrations in front of the bluff geometries, most notably in front of the trailer. In addition to this, it can be seen in the velocity streamline plots that for truck H, the roof deflector significantly improves the flow over the front of the trailer and reduces the turbulent region above the leading edge of the trailer. It can also be seen that the pressure contour plots and velocity streamline plots collaborate one another, as high pressure regions are present in locations where the airflow is disrupted by the truck's geometry, and as a result low velocities are apparent in these same regions. To conclude, 4 known aerodynamic improvements have been tested on an unimproved truck design with varying results. The roof-mounted wind deflector being the most effective in reducing aerodynamic drag, with cabin-mounted fairings and trailer side skirts being the least effective. The task now is to complete the truck and caravan combination simulations and write the report so that it can be handed in on November 12th, 2020. Thank you for listening.